people doing screen recording, because we are talking about having the department to actually pay for the wireless mic, USB mic, the tablet, and also having the necessary software purchased and installed on all instructor workstations. So that basically will lower the technological barrier, but we still have the psychological barrier. Some people just do not want to be recorded. So there's that. But I think most of the new faculty, do not mind doing screen recording. Some people have actually asked me what type of equipment I use, what type of software I use, and how I do it. So I'm pretty sure it will be more commonplace. It would just take time for certain people to feel comfortable to be recorded. Okay. All right, so in the share folder, in FX, final exam answers, there is this one, which is from the previous semester. It says, cisp310 Tuesday, Thursday, TT-FX, which is final exam. Unfortunately, I do not have the original one that does not have everything filled in already. Yep.
Does the 16 have any questions about structures?
The 16?
Yeah, you also have tests from 2016.
No. This is the first year, or first semester that I can actually get far enough to talk about structures.
Could you go over some examples?
Huh?
Could you go over examples today about a structure question that might be
Yes. So as I talk about these questions, I can kind of throw in, how I can turn it into something that has to do with structures. Okay. All right. So first thing first, your final exam is going to be here in this classroom from 8 p.m. to 10 p.m. on next Tuesday. So approximately 1 week from today. It's actually 1 week and 1 hour from now. So we are talking about 168 hours. Set your timer. Okay. It's going to be open book, open notes. Okay, so it's the same thing as your first and your second exam. Open book, open notes. You can bring a scientific calculator if you want to. Okay, I don't think it's going to be super useful, but if you want to bring one, that's fine. The one thing that I do recommend is to bring extra sheets of paper, because you might need extra pieces of paper. I would also recommend the use of grid paper. So this way, if you want to draw a picture of how the stack would look like, it makes it easier. Okay? All right. So let's go ahead and look at the first question. And what I'll do is I'm going to display the question, but I'm also going to hide the answer. So this way we can work on the solution in the class. Is that okay, or do you guys prefer just show me the answer and we'll be done in no time? Okay, this is better? Okay, all right. So we'll do it this way. So in this case, we are looking at a function in C, and we want to implement this in TTP ASM using the assembler language that we have been using for about 8 weeks already. Okay, remember at the beginning of the semester, I said that we'll be using assembly programming for the second half of the class, and that's kind of what we have been doing. Okay, so in this case, let's go ahead and start with this. The first thing is the name of the subroutine in C becomes the label that marks the entry point of the subroutine in assembly. Now that is not really just an arbitrary convention that I like to use, okay? Because if you want to write certain subroutines in assembly and other subroutines, you just kind of leave it in C and C++, and you want those things to work together in GCC, this is what you do. Okay? The name of the subroutine is really just a label representing the entry point of the function or subroutine. All right, so first thing first, I usually want to represent what is on the stack. So N is at the highest address, and then followed by A, which is a little lower, and then the stack pointer should be pointing at the return address like that. Okay, nothing new. Okay, we know the convention. Second parameter is pushed first, and then the first parameter is pushed last, and therefore it has the lowest address, and then we push the return address before we continue execution in the subroutine. Okay, Once again, this is the convention used by most compilers. So it's not really just in this class for the toy processor. It is used by GCC and most other compilers. All right, so now at the entry point, we have a local variable called result. Okay, so if I want to write this code, basically the same way so that, it's a direct translation from the C code, I'm going to do it the same way. In other words, I'm going to decrement the stack pointer, and we are allocating space for my local variable, which is called result. Is that okay? So the picture of the stack is no longer correct, okay, because now D is pointing to result, and everything is now 1 byte further away from where D was pointing to. Yep.
Sorry, Josh. In the stack that you made NA and the return address, which one is the top element right now in the stack?
On the stack, this is the one with the highest memory address, and right now, result is the one that has the lowest memory address. So if I were to draw the stack again, it's going to be N, A, return address, and result. And then the stack pointer is always pointing to the last thing that you reserve or push. So right now, it is pointing to result. No?
You didn't actually say one thing.
Oh, I forgot the D. The assembler would catch that one. It's actually kind of a challenge to make the spreadsheet catch all the mistakes because it's not a conventional lexical analyzer, so it doesn't actually have provisions to say, oh, I'm expecting this. I have to actually write special formulae to catch mistakes. Yep.
Just for when we're doing work on the functions, we're assuming you already established like the space and
Yeah, so when you write a subroutine like this, you basically have to remember all the conventions of when we call a subroutine, what is on the stack, in what order, and who is responsible to deallocate what. So all of those conventions need to be followed. Okay. All right, so now we are here. We need to implement the first assignment statement, which is result gets A. Okay. So now we have to figure out, okay, how do we get back here to access parameter A? Now, if you don't want to kind of remember different ways of doing things to access something that is on the stack, this is a template that is quite useful. The other thing that you can also consider doing is basically to add some numbers here. So you can basically say, how many bytes is each thing away from where D is pointing to. In other words, result is at 0 bytes away from where D is pointing to. In other words, D is pointing at that thing, okay? But when you look at the parameter A, which is what I need to get to, it is 2 bytes away from where D is pointing to, okay? So it might be helpful to number these items, so this way it is really clear how many bytes they are away from where D is pointing to. Okay, so right now I need to access A because it is the right-hand side of an assignment operation. So the template that works really well is to initialize a register A, B, or C. It doesn't matter which one, but I tend to use C in this case. And then you just add the value of register D, which is the stack pointer, to C. So these two instructions combined is going to compute the address of, in this case, parameter A. Okay. Now, I understand in the test you may not have time to do it, but if you do have time, I personally think it is really helpful to understand what register C is at this time. Okay. Now, if you don't have enough time, that's okay, but you can at least use some kind of graphical notation to say C points to A. Yep.
Wouldn't adding 2 point it to N?
Nope.
It's pointing at return address right now. So
Nope, it's not pointing to return address because I decremented D. So I reserved a byte on the stack for my local variable result already. So that means D is now pointing 1 byte below the return address. And that's why I redrew the picture on the stack. Okay. All right. So this is one of the things that I think many people probably encounter at one point or another is should I dereference or not? Okay, that's the question. Okay, am I having one too many dereferences or am I not having enough dereferences? So in this case, the right-hand side of the assignment operation is accessing the value of parameter A, and what register C has at this point is the address of parameter A. So that's not what I need yet. Okay, so it is really helpful to kind of remember that we need a dereference. Okay, it's like that. So after the dereference, C is actually parameter A, not the address of parameter A. Question? Oh, A, sorry. Yep. Okay, sorry about that. So register A is parameter A. Okay, I'm just going to make it really clear because they're both A's. And there we go. All right, so we got the right-hand side figure out. Now we need to get the left-hand side figure out, which is result. Fortunately, result is a local variable, and we only have one single local variable. So the stack pointer is pointing to result at this point. I don't need to do any calculation. Register D points to the local variable that I need to update. So that means at this point, a single store to what D points to is going to get a job done. So result equals to parameter A is now done. We are done with the first line of code in C. Is that okay? All right. Moving on to the second line. So second line is I need to decrease n by 1. Now, n is a parameter. So it's the same thing. How we got back to A is how we are going to get back to n. Okay. Now, if you want to, you can reuse register C. Okay. If you say that register C is still pointing to parameter A, we can just add 1 to it. That's cool. Not a problem. But if you don't want to do it like this, you can always just reload register C with a constant and then add D to C again. Okay. So, but since I'm just demonstrating different ways of doing it. So right now C is now pointing to parameter n, and it is not n that I really need. I need the value of n in order to increment it. So I need to do the same thing. Load it into register A, so that A is parameter n. Then I subtract 1 from that, decrement A, so that A is now n minus 1. And then I store that back to where C is pointing to. So now n is n minus 1, which is our decrement. Is that okay? Sorry? So increment C makes register C point to parameter n. The load instruction is going to load the value of parameter n to register A. Decrement A, so A is now parameter n minus 1. And then we have to store register A back to the location pointed to by C, because that's what I want to update. Okay, so that's basically minus n. And then we can decrement C again, so that it is the address of A. And then basically the same thing. If you look at the template here, this time it is parameter A. And then in this case, we want to do an increment because we're adding 1 to it. So A is now param A plus 1, and then we store that back so that we accomplish plus A in this case. So are we doing okay so far with the code that is on top of the loop itself? Is that okay? All right. So the loop says, as long as n is non-zero, okay, we do the following. So there are several ways to do it. Now, this is the part where, when you're writing this on a piece of paper, it can be a little bit more challenging because I tend to write my code in structures in a nested way. But when you're writing on a piece of paper, it is going to be a little bit more sequential. So you may not know how much space you need to leave in order to fit in every single thing inside the loop. So you kind of have to think of a way to do it. You can always just point it to another block of code. I can read arrows and follow those things. So you can, okay, I'm going to start up my tablet here. How much is a Surface Pro, like a brand new Surface Pro that is?
Too much. It's like
too much.
600.
Okay.
iPads have stylus support too.
I need a stylus support.
Yeah, yeah.
So is that how much are we talking about?
New iPads are 330.
Say again?
330.
330.
Yeah.
That's not too bad. I mean, $330 is not too bad.
Although that doesn't include the pen. That's an extra 100.
Oh, the pen is an extra 100.
You have to use the Apple Pen.
Well, no, but they also have the Crayola pen, which is $50.
Yeah, but you can't buy it.
No. It's legitimately called the Crayola pen. From watching that. They made an electronic type called the Crayola. It's awesome.
Oh, okay. So the reason I brought it up was because I was talking about this with the department chair, and we were evaluating different options of how to capture handwritten notes during class, and I just used. I mean, you guys know that I use this approach to capture handwritten notes, and then the question was is it worthwhile to get a Surface Pro to do the same thing, and
I use both Android and Windows for
Uh-huh.
note taking.
uh-huh.
I like it on Windows a lot more. I think if you're giving it to like teachers who haven't done digital pen stuff, I think they'd prefer the Surface.
Okay.
So, but like,
School budgets.
yeah, but if like it's not that bad on
Well, we already have a workstation, computer, and that's the thing, because if the professor comes in without any other devices, then I would say a Surface Pro is probably a better choice because it is a PC, and on top it is also a tablet. But because we already have a workstation computer, huh? Wacom? Do they have one where you can actually see what you're writing? They do have one, but it's expensive. Yeah.
No, I was recommending Wacom without the display.
Those are harder. Yeah, I would agree they're actually quite a bit harder because you don't know, you have to look at the screen and then, your hand is, down there, so positioning is a little bit more tricky. Okay, so getting back to here. So what you can do is, during the test, is you can write down your label like this, okay? Do some code over here, and then you have an unconditional branch back to begin while, and then you have the end while label here. And then, then you can just use a symbol, like an arrow, to insert code that goes into that block, okay? And you can do the same thing, if this block here is a conditional statement, same thing. Write the framework first, and then use an arrow to put in other code within that. So you can basically, quote unquote, do insertion, on a piece of paper. So this way you don't have to write your code in a linear fashion anymore. Yep. You can, but you have to clearly indicate which block goes where. Where is the insertion point to which block? In other words, yes, you can use a splitter and a tunnel in your in your answer. So basically, in this case, you can basically label this block. Let's say you label this block A, somewhere else on the piece of paper, and then over here you basically refer to A. So you're using the concept of a tunnel. When you use A, A is kind of like a tunnel, but when you abstract a block of code, to a single symbol, it is kind of the job of a splitter, because you're merging a bunch of wires into one single, item. So you can do it like this. That makes it easy for me to follow, but also at the same time for you guys, it's easier to write your code in a structured way, in a nested way. So, that's just an idea, okay, of how you can write this code, but without, and also keeping track of the nested nature of that code. Okay, but since I'm using an editor, I can just, kind of do it the other way. Begin while. There's a reason why I do it this way, basically, because if it's a while loop, there's always a JMPI back to begin while, and now I need to think about, okay, so how do we get out of the loop? Okay, So now I can just focus on one thing, which is, okay, let's check n. Is it a 0? If it is a 0, let's get out of here. So I'm only focusing on one control structure at a time, and that really helps me focus on just one thing to deal with at any time. So it doesn't matter how complex the really overall program is, I can just focus on one thing that is relatively simple at a time. Okay, it's the same deal. If you don't want to keep track of where C is pointing to at this point, just do another LDI. Okay, so you look at this picture and go like, I need to access n. Oh, it's 3 bytes away from where D is pointing to. So you load 3 into C, and then you add to C what the stack pointer is. So at this point, C is the address of n. But we are not comparing the address of n to 0. We are comparing the content or the value of n to 0. So we need a LD instruction. So my usual way of doing it is to put it into a different register because I might want to reuse C later on. So register A is n at this point. And then I'm going to use this trick to set the Z flag without a single compare. Because the AND operation goes through the ALU, it changes 2 flags for sure. It changes the Z flag to reflect whether register A is 0 or not. It also changes the sign flag. So if the most significant bit of A is a 1, then the sign flag is going to be a 1. In other words, the sign flag is the most significant bit of register A after the AND operation, which can come in handy. In this case, it's not useful, but in certain other cases, it can be handy. Okay, so now we can use a JCI instruction because the Z flag is set or cleared. It is modified by the AND instruction. So if it is 0, we go to AND while. Okay, so right now we have the control structure done, and now we just need to deal with, okay, what is inside the control structure? Well, we have a conditional statement, and then we have 2 additional statements to change values of the parameters. So at this point, I can focus on the conditional statement. If whatever result points to is greater than whatever A is pointing to, we change result to become A. Okay. Now this one is tricky a little bit. It's a little bit tricky even in C because we are comparing what they point to, but the assignment is not what they point to. Okay. So you have to kind of make it clear in your mind what the C code is doing first before you translate that into assembly code. So I'm going to do it the same way, which makes it very lengthy, but this is kind of the sure way of doing it. Okay, so we'll do LDI. We need to access whatever result is pointing to. That's the easy one. Okay, we just need a LD AD. So A is result, and then LDAA. A is now whatever result is pointing to. Is that okay? Because register D is the stack pointer, it is still pointing to the local variable result. And then I'll use another register for the other one. The other one is whatever A is pointing to. So according to this map, A has an offset of 2 from where the stack pointer points to. So we load B with 2 in this case, and then add BD. So the register B is now the address of parameter A. LD, okay, BB. B is now parameter A. And then one more, BB. B is now whatever parameter A points to. Is that okay? Yep.
So we allocated a result, right? So the address of result was 250 something, or 252, or somewhere around there, right?
Well, we don't know where it is because by the time this function is called, the stack pointer can be all the way down to maybe 100.
Well,
Yeah.
So it's somewhere. Right?
It is somewhere,
It's
right?
somewhere that we allocated.
Yep.
And so when we dereference that,
Yep.
how do we know where that's going to take us?
You mean result?
Yeah, result. So let's just say arbitrarily that
It's not arbitrary because we already initialized it earlier. So the result is the same as A. So it is not uninitialized.
Okay.
Now it does potentially change as we execute the code in the loop, but it is not uninitialized. Yep. Okay. So now we can compare these two. So whenever you compare, you have to kind of evaluate the two options because you can compare A to B. Okay, you can basically A minus B, or you can also compute B minus A. One way is usually more handy or more convenient than the other one, but you can usually make either one work. Okay. All right. So in this case, we are looking for an excuse to get out or bypass the then branch. Okay. So that means we are looking for whatever result is pointing to being less than or equal to whatever A is pointing to. Then we want to say, okay, let's skip the then branch. So that means, compare AB makes more sense to me. It doesn't mean the other way around doesn't work. Okay, it is just that this seems to make more sense to me because I'm always looking for excuses to bypass the then branch. You can do it the other way, to go into the then branch and then an unconditional branch to go around the then branch. That works too. Okay? So there are many ways to do the same thing. So if I compare like this, then I go like, if it is less than, let's go around. So now it depends on whether we're doing signed comparison or unsigned comparison. These are all ints, which means they are signed. So a JLI to end if. Make sense? So end if is basically marking the end of the conditional statement. I'm just going to put a label over here. But then I also have another excuse get out, JZI also to end if. In other words, I'm saying if register A is less than or equal to B, we get around the then branch to end if. Is that okay? All right. So now whatever is in between here, okay, between the JZI instruction and the end if label is the actual then branch. Yep.
In the code, it's just greater than.
Yep.
You said it was going to be greater than or equal to?
Less than or equal to.
Oh, less than or equal to.
Because we are looking at the negation of being greater than. Because if it is greater than, you go to the then branch. But if it is less than or equal to, you go around the then branch and you skip over the entire thing. Yep. Mm-hmm.
Could you also rewrite it and say pointer A is less than pointer result, and then load your registers in that way, and then only
Yeah.
use JLI?
Yep. You can. There are several ways to rewrite it. Yep.
Isn't, I know it may not be a good question, but in the stack, isn't D pointing to the result right now?
Yes, it is.
So why did we come and put D into another register, then do a comparison? Instead of just putting D into A, we could just put.
Are you referring to line 32?
Yeah, line 32. Why
And
couldn't we just use the comparison as a, like an A and D and see what happened? Why did we have to load D?
Because it's the dereference. We're looking at the
yeah,
value on D, not D itself.
that is correct. So the dereference, you cannot combine dereferencing with compare. I think that's what you are asking, right?
Why did they just use D instead of just loading D into A, then using A?
But this is important because I'm dereferencing what D is pointing to. If I do a compare D over here, it is comparing register D, which is the address of result, to what B is. But I don't really care about the address of result. I want to know what it is pointing to. So that's why we need not only one dereference, we need double dereference. The first one gives me the actual value of result. The second one gives me the value of what result is pointing to. Mm-hmm. Any questions? Yep.
For line 34,
Uh-huh.
could we just load B to D and then increment it twice?
Yes, you can. Yep, same thing. CPR, right? So you're talking about CPR. On line 34, you can redo this by a CPR BD and then increment B, increment B. It will do exactly the same thing. But I'm trying to be consistent, because this is kind of like an easy template for people to remember. In fact, you can just kind of write down on the cheat sheet and say, if I know the offset from where the stack point is pointing to, I just use these two instructions to get to the address of that thing. So that makes it easy for certain people to kind of just remember there's one way to do this instead of, oh, this is a more efficient way to do it. Yep.
Correct me if I'm wrong, but if we did compare BA, that would be A minus result.
Uh-huh.
Couldn't we just do JLI?
Yes. But then then you need two labels because you need a JLI to the beginning of the then branch, and then you have a JMPI to end if. As opposed to this method only has one single label. I mean, we're not looking at optimization here. They're both about the same speed, but in terms of just being consistent, of looking for reasons to go around the then branch, this is just be consistent with that. Is that okay? All right. All right, so inside the then branch, we have result equals A, okay? So we need to go back to A again, okay? So according to this map, we haven't changed the stack pointer, so A is 2 bytes away from where the stack pointer is pointing to. So this time I'm going to use the other approach, okay? CPR, AD, increment A. So now A is the address of A, parameter A. So I'm just trying to make it a little bit more clear, which is not exactly what I need. It is leading to what I need because I need a LDAA in this case. So the A becomes really just parameter A. That's the right-hand side of the assignment operation. And then the left-hand side, once again, is easy because register D, the stack pointer, is still pointing to result, which is the last thing that I reserved on the stack. So it's a single store instruction to whatever D is pointing to, A. So this is going to be doing result equals A in C. Are we doing okay so far with this? So far so good? All right. So now I go to end if. There's nothing to do after the end if except for these two things, okay? So this is where I can be a little bit lazy, and it's a little bit harder for you to be lazy in this case. You can, but it is, you need to clearly indicate the labels because, at this point, I am just, I cannot do it. I cannot do it because register C doesn't have the proper value, so I cannot just copy and paste that code. Which is okay, we'll just spell out the code and it's okay, not a problem. So we need to find n first. N is 3 bytes away from where the stack pointer is pointing to. So LDI A3 add AD. That would be the address. Okay, so let me just kind of write down the comments here too. This is A is now the address of parameter n. So we do a LDAA. Nope, I cannot destroy A. Okay, A is actually useful at this point. So B is the actual parameter n. I need A back because I need to store it back to that location. So I need to do a decrement B and then a store back to A, B. So together, these 5 instructions is doing minus minus n. Is that okay? And then the other one, I'm just going to be a little bit lazy this time. Copy, paste, and modify. Because this time we need to access parameter A. But instead of decrementing, we are incrementing. And I'm updating the comment so it is actually correct. There we go. Huh? Oh, plus, plus, that's right. Okay. There we go. Yep. Line 44. Why would I need another increment? Oh, you're right. Okay. Yep. Good point. So the command is actually incorrect because this is the address of the return address. And now it is the address of parameter A. Thank you. Good catch. All right. So we are done with everything inside the while loop. And oops. So after end while, we got two things to do because we need to do the usual return, but we also have to specify the return value. The return value is in the local variable called result. Register D is still pointing to result. Okay, so LDAD is going to say use result as return value because when we want to return a value to the caller, it is through register A. So that's why we are setting register A. At this point, I can do an increment D because we are deallocating the local variable result from the stack because I have no use of that local variable anymore. LDBD is to retrieve the return address to register B. And then we increment D again to deallocate the return address because it is the callee, the subroutine's responsibility to free or deallocate the return address from the stack. Okay? And then finally we say, okay, since register B has the address to go back to, we'll just do a JMPB to continue execution in the caller. So that's basically how this C code is implemented in assembly. Do we have any questions about any part of this code? No questions? Yep.
Do you think we're going to have 5 questions on this test, or are you going to make it more questions?
I have not decided yet. Undetermined, to be determined. TBD. Yep.
So right now, at the end while how do we know if D is at the return address?
So what we do is we look through this stuff here, and we ask, did we do any changes to register D, basically from here all the way back to the beginning, since we allocated the storage for result.
Implemented it once.
You mean register D?
Yeah.
No, I don't think so. We decrement it. So the only thing we did inside the subroutine is to decrement D once to allocate for result. But after this, we have not changed register D at all. So register D basically keeps pointing to result for the entire duration until we get out of the loop. Yep.
No, just saying at the very end, A is holding on to the result.
Yes. Because that's also a convention, that we said, remember we said that register A is the register to contain the return value if a subroutine is to return a value. Yep.
Are all the questions on this practice test applicable to the questions that are going to be on our test?
So in your test, there will be a question that does not have structures, kind of like this. But there will be one, at least one with structures as well. Yep. Yep.
What is the likeliness of it being this long?
Um, well, it is kind of lengthy, because I talked a lot. But if you look at the actual code, this is basically the code, so it's not, this one has a little bit of optimization. I kind of keep track of where C is pointing to. So it's a little bit more optimal, but it's not really that long. I mean, you figure if okay, this is not saying that I am going to give you 5 questions, but if there are exactly 5 questions, you have 2 hours, 120 minutes. So you have 24 minutes per question. So, and questions like these is kind of nice in a way because there's partial credit. So let's say you set a timer for yourself, 24 minutes per question, and you got through to, say, here, okay? So I'm just going to grade, based on what you have written up to this point, and I'm asking, do you understand how a loop works, okay, the structure of a loop? Do you understand how to dereference A and result? Do you know how a conditional statement works? And so on and so forth. So by the time you get here, you get most of the partial credit already. And when 24 minutes expires, you move on to the next question. But you will still be getting a lot of partial credit for this. Because this is not a quote unquote practical exam where you actually have to write the code, it has to run correctly to get any points. It is just on paper. So I'm just visually going through your code to see whether there's evidence that you understand how to access parameters, whether you understand how to dereference parameters. Can you differentiate, getting the value of a parameter versus what the parameter is pointing to? Do you know how to compare? Do you know how to formulate a loop, like a while loop? Do you know how to formulate a conditional statement? Do you know how to nest these constructs and so on and so forth? So if you basically stop at this point, you will not get the points for, oh, do you know how to return a value? Do you know how to actually return to the caller? So you will be missing those points, but you'll be getting most of the other points. Yep. So that's also a strategy that you might want to consider, is to have a timer. Okay, and I wouldn't set it to 24 minutes. I would set it to 20. So this way, at the end, you have some time to go over some of the questions that you might want to go back to. So you set your timer to 20 minutes. So let's say there are 5 questions, you have 2 hours. So that means you have 5 times 20, which is 100 minutes. So now you have quote unquote spare, a spare of 20 minutes to go back to a question that you thought, oh, okay, I didn't have enough time to finish this one. Now I have time to go back to try to finish that. Is that okay? Yep. That's a good question. Well, okay, this is what you can do. Write down the start time of a question. And then you just look at your watch. You can pre-compute when you need to move on. So occasionally you just look at your watch and go like, okay, is it time to move on? If you have a Fitbit, Fitbits can have silent vibrations, so it would just kind of buzz you, and it shouldn't disturb other people. Unless you guys want me to make a mechanism to beep every 5 minutes.
Yes. Yes.
I think that increases the anxiety level. Okay, so this is the other code, other type of program where I give you the assembly code, and you tell me what it should look like in C and C++. Okay, basically the reverse of the first question. Okay, so when you look at a question like this, you go like, holy smokes, where do I start? Okay, identify things that you know what they do already. Okay. The one way is to kind of linearly to do it. The second way is to do it in a structured way. It's up to you guys to decide how you want to do it. So the way I do it, okay, so let me kind of clear out all this stuff here. I can do it either way. So you can basically say, okay, here's a subroutine. It potentially has a return type of some kind, sub1, and we don't know whether it has parameters or not. And this is the general template of the subroutine. Now, you may not be able to do it like this in a test because you're writing on a piece of paper. It's kind of difficult to kind of backfill stuff. But you can kind of jot down notes. Okay? You can jot down notes on the exam itself. So that way, if you run out of time, I can still look at your rationale, your reasoning, so I can at least tell that, oh, okay, so you know how to figure out whether there are parameters or not. Or you figure out how there are 2 parameters, which is significant, okay? So whatever your reasoning is, okay, just kind of write it down on the exam itself and turn it in, okay? So if I write this code, if I look at this code, from the start, and go like, oh, here's a decrement of register D, and I'm not storing anything to what register is pointing to right away, what do you think that's telling you? I have some kind of local variable, okay? Or it's a very clear, or it's a good sign that we have some kind of local variable, okay? So we have some kind of local variable, local var type, which I don't know what it is yet, but there's a local variable of some kind, okay? Okay, so moving on, from the assembly code, the first thing is I'm incrementing I'm incrementing register C, but register C has the same thing as what register D had before the decrement. So line 2 is making a copy of register D to register C. On line 4, I'm saying, okay, let's bump it up by 1. What do you think register C is pointing to, and what is the implication to the interface of the subroutine? We have at least one parameter, okay? Because by the time we get to line 4, C is the address of the first parameter, okay? So that means at this point, I know there is some kind of stuff here, okay? So we just say it is some type. I don't know what type it is, but we know that there's at least one parameter, okay? So moving on, line 5 is retrieving the parameter itself. And then line 6 is dereferencing the parameter. Yep.
So it's that one because when we go into the call function from main, we're passing from right to left over, right? That's why it's the far left argument in the function's actual definition.
So the convention is we push the last parameter first, and because
So the closest thing to the stack pointer is the first.
the last thing you push has the lowest address. So that's why we're accessing the first parameter at this point. Now we don't know how many parameters are after that, but we know for sure there's at least one, and we're accessing the first one now. Okay. All right, so getting back to this code, on line 5, we are retrieving parameter into register A. On line 6, we are dereferencing parameter 1. So what is that telling you about the type of param 1? It's a pointer of some kind. Now, is it a pointer to a signed integer, or a pointer to an unsigned integer, or is it a pointer to another pointer? We don't know yet, but we know it is, at least it is a pointer, because we are using it as a pointer. We are dereferencing it, okay? All right, so line 7, we are incrementing C again. So C, before line 7, C is pointing to the first parameter. By incrementing C and dereferencing C on line 8, we have a second parameter now, okay? So we know for sure that we have at least 2 parameters. So we'll say, some type, and then param2. I don't know whether param2 is a pointer or not yet, okay? But then I look at line 8 and 9, and go, line 8 is retrieving param2 into B. Line 9 is dereferencing param2. Oh, so param2 is a pointer as well. All right. So we basically say, okay, param2 is a pointer as well. And now we compare A and B. Now, whenever we do a compare, there's a very good chance that A, B are integer types, okay? It's not like we cannot compare pointers. We can compare pointers. Pointers can be compared. But most of the time when we're comparing, we're probably comparing integers. So there's a pretty good sign that we are comparing integers. The next line, line 11, is telling you for sure what we're dealing with, because it's a JLI. So if it's a JLI, what do you think is the type of register A and register B? Signed integers. Okay, there's no escape from this one, because otherwise I would be using JCI. So now we know register A is a signed AB integer, register B is a signed AB integer. But wait, those are the things that are pointed to by param1 and also param2. So now we have just resolved what is this sum type here. It's an AB integer here, and it's also AB integer here. Now in the test, if you don't want to write int 8 underscore t all the time, I would just take int as an implicit A bit, or unsigned as an implicit A bit as well. So there's no need to specify the width unless you really want to emphasize this is 16-bit wide or something other than 8-bit wide. The cricket is back. Yep.
How do we know that they're both signed integers?
Because of the JLI. Because the JLI is applicable to the result of comparing AB. We're only paying attention to the L flag in order to decide which way to go. So that means, whatever I'm comparing, I should be interpreting those as signed integers. Okay?
I see, yeah.
Mm-hmm. Okay, cool. And then we also have a JZI to the same label. Do you guys recognize this? You know, JLI or JCI followed by JZI? We just did that. Okay, so you start to recognize blocks of code together that means something. Okay, so it is basically, the first question is, can you convert C code into the smaller chunks of code? This is basically asking you, can you look at small chunks of code and recognize what it is in the high-level language? Okay, so in the C code, we know what we're comparing. We are comparing whatever param1 is pointing to versus what param2 is pointing to. What we do not yet know is, first of all, when you look at a condition, there are only about a few contexts where we need to evaluate conditions. I'll give you 5, okay? But out of the 5, 3 are in the same family. The other 2 belong to the same family as well. You have loops, right? Because in a while loop, you have to evaluate the condition to decide whether to stay in the loop or not. That's one application of a condition. You have a do-while loop, which is kind of the same thing, except the condition is at the end of the body of the loop and not at the beginning. And then you have 3 different types of conditional statements. There are only about 2, but I'm going to call it 3. The first one is a if, but no else. Okay, you only have a then branch. If the condition is false, you just kind of continue after the conditional statement. The second one is an if-else, which means you have a then branch as well as an else branch. And the third one is a ternary operator, where it is not a statement, it is a operator. But it still has a condition and then 2 values to specify depending on the condition. Is that okay? So when you look at a condition like this, okay, because this is clearly a condition, okay? A compare followed by conditional branches, that screams, I am a condition to you, okay? So what we don't know is the context. So when you do not know the context of this condition, you can at least rule out things that it cannot be. Okay, so let's try to rule out things that it cannot be. Can it be a loop? Can this condition be utilized in a loop? We got 2 types of loops. We have a while loop. If it's a while loop, what makes you think that this is not the condition of a loop? There's no label before the compare. Okay? If this were the condition of a while loop, there would have been a label before the compare so that we can go back to that point. Okay? It cannot be a do-while loop either, because even with a do-while loop, we have to have a label that's defined earlier so that we can go back to an earlier point. So we know this is not a loop. So now it is one of the 3 conditional things that we can have. We can have so now of the 3 conditional things, you can kind of, just kind of imagine there's an if here, okay? And then you have to decide, so an if for sure has a then branch. So now the question is, do we have that optional else branch? That's the question. All right. So maybe at this point it's not particularly clear, so let's check it out. L1 is all the way down here, okay? So either L1 is the end of the conditional statement, or it is the beginning of an else branch. It can only be one of those 2 things. Okay? What is the telltale sign that can help you differentiate between an if versus an if-else? Yes?
I think it is an if-else because right before the L1
Yep. It's an unconditional branch. Exactly. So very good. So on line 22, which is right before the label that can be either an end of condition, end of then branch. Excuse me. Okay, let me roll back. So L1 can either be end if, okay, to mark the end of the entire conditional statement, or it can be the beginning label of the else branch of a conditional statement. So we have to differentiate which one is it. But the unconditional branch on line 22 to branch really just around what L1 starts is telling you L1 is the beginning of the else branch. Yep.
Just like kind of a recap. We know that it's an if-else because there's no labels, so it can't be a while.
There's no label before the compare. There's no point to jump back to. So that's how we know this is not the beginning of it's not the condition of a loop. Yep.
Oh, what if like in the final answer, we pretty much got like the same like result, like from the if and else branches, but we switched them around.
You can switch it around, okay? So because the meaning is more important than the actual ordering. So you can interpret this as the then branch, on line 24, you can interpret that as the then branch, and then this big chunk here from line 13 all the way to line 22 as your else branch. You can flip it, but if you flip the interpretation of the else versus the then, you would also have to flip the condition that you're looking for. So if the original one is less than, then you have to specify greater than or equal to. Okay? All right. So, but using the usual way of doing things, the later one is the else branch. So in the else branch here, what are we doing with the else branch? We're putting a 0 into register A, returning 0, okay? Because register A is used to specify return value. So we know there's a return 0 here. Cool. So now we just have to figure out what is the then branch doing, okay? All right, so the then branch is starting on line 13, and it starts right off with a store instruction to whatever D is pointing to. Tell me again, what is D pointing to? Yep.
Well, at the moment, he's pointed at the return type. Can we also assume that the return type is also an int?
That we do not know yet. Because a 0 can also be a null pointer, so we're not quite sure yet, okay? Yep.
Why is the return 0 in this branch? I don't get it, because like it seems like it's saying like if the L flag or the 0 flag is set, then do this, else fall through to the stuff that it jumps.
So we are looking for excuses on line 11 and line 12. We are looking for reasons to branch to L1, right? So at that point, we cannot tell whether L1 is the end of a conditional statement or whether it's the beginning of the else branch. The indicator that L1 is the beginning of else comes from the unconditional branch right before that, because that's the pattern of a if-else type of statement. Is you need some way to, at the end of the then branch, you need a way to get around the else branch, because otherwise it will follow through the execution, which is not what the C code is indicating. Okay, so we are storing something to where D is pointing to on line 13. Where is D pointing to? The local variable. Okay, so var1 is getting something, and it's getting whatever A has. So when you look at the compare on line 10, what is A containing at that point? Whatever param1 is pointing to. Okay, so we can just put it here. Oh, by the way, I haven't really finished it yet. What is the condition, or what is the comparison that is in here? What do you think? If it is less than or equal to, we go to L1. So what is the condition to continue with the then branch? Greater than. Okay, yep.
Doesn't register A have the param2 second?
No, register A has param1, because register A is getting, we got to register A first, and then we increment C to get to register B. So A is what param1 points to, and then B is what param2 points to. Yep. All right, so we are now done with that one, and we continue our analysis to line 14. Okay. So line 14 says decrement C. So this means you have to kind of keep track of what register is pointing to. Register C was pointing to param2 prior to line 14, so now it's pointing to back to line param1. Okay. So C has param1. It points to param1. Okay. So on line 15, A is param1, and then on line 16, we are storing B to whatever A is pointing to. Wait, A is param1, so we are storing B to what param1 is pointing to. So that means on the next line, the left-hand side is whatever param1 is pointing to. What is B? I haven't changed B since line 9. So did you guys keep track of what register B had? Whatever param2 has, right? Okay. I think you guys are starting to recognize this code. And I think most of you can guess what the next line is. Okay, but we'll work it through anyway. So we are done with line 16. Okay, so we're moving on to line 17. So on line 17, we increment C again. C was the address of param1. Now it is the address of param2. We load the address of we dereference the address of param2 to register B. So B is now param2. And then we store to register B on line 20. So in C code, it means we are storing to wherever param2 is pointing to. Okay, now we have to figure out what are we storing to it. On line 19, we are dereferencing register D, which is our stack pointer. What is our stack pointer pointing to? The local variable I just call it var1 because I don't know the intention, so I just call it var1. So register A after line 19 has var1, the value of var1, and we are storing that to whatever B is pointing to. Oh, okay. I hope that looks kind of familiar. That's from your swap subroutine, okay? But we're not done yet. There's a line 21 that is kind of odd. There's a return 1 here. That is a good indicator that the return type is an integer of some kind. Now, is it signed or unsigned? There's no indicator, okay? So unless you do a compare, and then you do a JLI versus a JCI or something like that, there's no indication in this case whether the return type is signed or not signed. So in that case, either would consider to be correct answers. Yep.
If it was a JCI, then would that be
But then you're applying that to the return value, which is unusual. Is that okay? So in the absence of any indication whether it is signed versus unsigned, either one is fine. Okay? If you say it's unsigned, I'll give you full credit. If you say it's int, I'll give you full credit. Even if you say it's a char pointer, I'll give you full credit. Because it's a scalar. Yep. You first and then you. Yep, go ahead.
Would it be okay to say bool in this case since it's 1 and 0?
Bool? There's no bool in C. Yep. Okay. I think in C++ there's bool, but in C there's no Boolean type. Yep.
Say var1 is an int, right? It's stored in integer variable, which is the dereference of param1.
Right. So you can also infer that local var type is int at this point. Yep, you're correct. Yep. Say again? Which? var1 is not a pointer. Because var1 was storing whatever param1 is pointing to, so it is not a pointer. Yeah. Cool. So is that okay? So, you can see how this is the reverse of the first question in terms of what it's asking you to do. So are we good so far? Okay. So instead of asking you something like this, I can be asking you to reverse something that has structures in it. But then I will give you, prior to that, I will give you the structure definition so that you know the offsets of the structure to the individual members. Okay? All right, moving on. Question 3 of 5. I'm not going to answer this question, at this point because we are running out of time, but oops, sorry about that. Yep, my wife has a priority over the do not disturb. So that might actually be important. If she calls me again, I might need to pick up the call. Okay, question 4 of 5. I think I'm not going to ask you questions like that. Okay, sorry. I'll answer the phone, but I'll be brief. Hello? 喂 ？OK，唔緊要，因為屋企電話 forward 咗俾我嘛。哦，OK，我諗佢係俾成班㗎，咁樣所以，嗯，我諗睇翻屋企問咗佢先啦。OK，好啦，OK，拜拜。OK，I apologize for that, and that's also recorded in the recording, but it's in Cantonese, so you know. But you'll be surprised, how well YouTube can translate. Because it's not unusual that I would actually use a Google Voice search, and I would use part English and part Cantonese, and it would actually pick up which part is English, which part is Cantonese, interpret the question, and actually find me the answer. I can tell you what it was, and it was not an emergency. It was about buying donuts for my son's birthday. Okay, but my wife was actually calling home, but I programmed my the landline, to simultaneously ring a bunch of other phones, which includes my cell phone. So that's why it was ringing. It's kind of like pointers, right? So the landline dereferences to my phone. See, I can make that relate to this class. Huh? To do what? Right, but the call is going to my landline at home. So I program my Sure West or Consolidated Communication Now to simultaneously forward the phone call to different cell phones. Yep, broadcast, shotgun. Yep.
Do we need to understand the micro slices of how the opcodes work in the microcode slices?
Say that one more time.
The microcode slices and
The microcode slices? Yeah, there's one question like that. I think this is the question that has to do with microcode. Which instruction relies on the combination of blah blah and blah blah? So that's a microcode slicer kind of question.
Will that be on this one?
I'm gonna take it out. So microcode is not gonna be in the final exam because we are covering a little bit more material than last semester because we got structures. So it's only fair that I take out something to make room for structures.
Can you make that a promise?
Well, it is recorded. That's the best part of being.
JavaScript, you can't make promises.
But if you program in Perl, you can bless. Yes. Yes, there's a keyword called bless in Perl. That's how they do object-oriented programming. So you start with a hash, which is just a mapping, and if you want to turn it into an object that has a class to belong to, then you use the class PM file, Perl module file, to bless the hash object. Once it is blessed, now it is linked to the quote-unquote class definition. But you can also bless an object multiple times. So then it becomes, you have a polymorphism, like that. It's really kind of cool. And you can do all of that stuff at runtime. So you can choose whether to bless something. I guess in real life, people can do that too. But you can choose whether to bless something at runtime. So whether an object is actually blessed or not, is entirely a runtime thing. It's not compile time determined. Cool. Okay, this is question number 5, and just from the use of arrows and colors, it seems difficult, but it's not. Okay, so I may not have enough time to actually work out the entire code, but I will give you the strategy of how to approach this question. But first of all, I'm just going to copy the whole thing. So sub1, 2, and then in parentheses, sub2, 20 is less than sub3, question mark, 1 plus sub4, 11, close, close. And then we got a colon, 0, a 3. Okay, there we go. All right. So when you look at something like this and they say, okay, go ahead and implement this statement in C in assembly, you go like, where do I start? This is a whole bunch of gibberish. Well, it's not, okay, because we have seen all of these constructs already. You have to kind of figure out, if you are to do this by hand, how would you do it? Okay? So the first thing is to figure out the nesting of all of these things. What do you need to do first, and then what, and then what? The dependency of things. You can see, the outermost layer is sub1, is a function call, right? Can you call function sub1 like right away? Can I do it first? It's the very first thing I do. Nope, because in order to call sub1, you have to first figure out all of its parameters, right? All of the arguments. Okay, in this context, it is arguments. Okay, well, so it looks like sub1 has some, arguments. How many arguments can you identify? It has got 3 arguments. Okay, just by looking at the nesting of the parentheses and whatnot. Okay, this one is pretty clear. So 2 constant as a constant being the first argument to sub1, pretty darn clear. The second argument looks really long. Okay, it goes from here all the way up to here. But nonetheless, it is an expression that gives you a single value that you're going to use as the second argument to sub1. Okay, and then it has a third argument, which is a constant of 3. Okay, so it looks like the most complicated part is going to be this portion here. So when you look at the middle portion, what is it at the top level? It's a ternary operator. Very good. So this is the first portion, which is the condition. This is the second portion, which is what I call the then value. And this is the last one, which is the else value. Okay. What is the first thing you're going to do with this particular thing? Push 3. Okay, because we eventually we want to prepare everything on the stack to call sub1. So that means you have to push 3 first. Even before you do the ternary operator, push 3. Okay? Because the overall idea is push the last argument, push the second argument, push the first argument, and then call sub1. Okay? So we push 3 first. After you push 3, what do you do? It's a big mess here. Okay? I'm going to highlight the big mess. But the big mess is nothing more than a difficult to read kind of conditional statement. This part is the condition. You have to evaluate the condition first in order to determine, do I want the then value or do I want the else value? Huh? And all of those are calls, yes. So then you have to evaluate, you have to figure out the return value of sub2 of 20 first. But that's just calling sub2 with an argument of 20. Do we know how to do that? Push 20, push the return address, continue execution in sub2. After it comes back, clean up the stack, okay? Because 20 would still be on the stack that is useless. Clean up the stack, okay? And then we have to call sub3. That would be my ring, telling me that somebody is at the door or garage. You can see all the notifications that I'm getting, right? There's no way to escape. But there's one thing that is important. Before you call sub3, there's one thing you have to do. Because what we're doing is we're comparing the return value of sub2 20 against the return value of sub3. Okay? You got 2 adjacent function calls. Both have return values. And the return values of both are important. So what do you have to do to get this to work correctly? Yep. because right after sub220 returns, you clean up the stack, but then you have to push the return value on the stack. Because when you call sub3, register A, B, and C can potentially be updated. So you cannot rely on those registers still containing the values that they had. In fact, in this case, we know for sure that register A is going to be overwritten by the return value of sub3. So you're going to lose the return value of sub220 if you do not push it on the stack. Is that okay? So you call sub220, after it returns, you clean up the stack, then you push the return value on the stack. Then you call sub3, okay? Sub3 returns, you pop the return value from the stack into a different register, let's say register B. Then you compare register A, B. Then you use conditional branch to decide, okay, am I going to specify this value and push it on the stack, or am I just pushing 0 on the stack? It becomes a conditional statement kind of thing, except it is an operator. Is that okay? Yep.
Is there any reason why you have to push 3 first and can't evaluate that ternary and then do all 3 numbers at once?
You can do that too, but since I'm lazy, I'm just using the shortest sequence of code. Because you have to push the 3 anyway, you might as well just push it first, go through this computation. When you get to the then value, push that on the stack. If you get to the else value, push that on the stack. Then these 2 branches will merge, and then you push the 2 on the stack, and then you call sub1. And then after sub1 returns, you still have to deallocate the 3 arguments that are now on the stack. Then you're done. Yep. Say that one more time. Well, you can. So what you can do, is to first evaluate what the middle part is, stash it into a particular register, but don't push anything on the stack. Then you push the constant of 3, you push whatever the value of the register has, you push 2, you can do it that way too. But that means, you need to store whatever you need to push in the middle into a register first, and then you push the 3. So I just kind of do the reverse, which is just push as I go along, so that by the time I get all the way back to sub1, I can just do the function call. So it looks nasty, but when you really break it down into smaller chunks and then smaller chunks and then smaller chunks, you can figure out the ordering of what needs to happen first, what needs to happen next, and so on. Is that okay? The solution, even though I don't have enough time to really go over the solution, live, it is here already. And then I use this notation to help identify this 20 is pushed here, and then the call of sub220 is the entire blue thing over here, and so on. So if you kind of read it this way, I know it's kind of messy because of all the lines flying around, it still indicates what I said earlier today. Is that okay? All right. The homework assignment is due tonight for the second lab, for the late lab. The early lab is due already. The solution is going to be discussed tomorrow on my Wednesday class during the lab time. So if you watch the video of the lab time of my Monday, Wednesday class, you will get to see the presentation of the solution of that homework assignment. Yep.
When is the lab putting the time for is it in the lab or
I think it's before the lab. I cannot remember. If it's after the lab, I would do the recording at home. All right. So I'm just going to clean up here and go to the lab with you guys.